An important aspect of QueStech innovative training network is the collaboration of partners from academia and the industry. Here in San Sebastian, for example, the early stage research from CIC nanoGUNE and Graphenea are working closely together on common topic, being 2D materials and spintronics. So while each one of us has his own individual PhD project, we can profit from the synergies coming from the collaboration of the two research centers, and we can discuss over common challenges or over common expertise that we gain working on common topics.
2D materials are a novel family of materials that have been discovered merely 10 years ago. Graphene is probably the most well-known and the most prominent of these. However, there are other 2D materials such as TMDCs, transition metal-tical cogenite, which offer semiconducting properties, and insulating boron nitride, which very much complement those properties of graphene. These materials are truly a single crystalline monolayer, and we can synthesize these nowadays, but this was thought to be impossible. Here at Graphenea Semiconductor, we focus on scalable processes such as chemical vapor deposition to deposit graphene and other 2D materials. What we do is take these materials from the lab to new applications and new markets.
The interest of our research group at CIC nanoGUNE is to combine different 2D materials and van der Waals heterostructures and exploit their unique properties for spintronic application. The idea behind spintronic is to not only use the charge of the electron, but also its quantum mechanical property of spin. There's a wide variety of device designs that could be used in the future, and it could be better than existing technology in terms of processing power or power consumption. But before we can build these devices, we have to investigate the fundamental principles and phenomena that happen at this atomic scale world. One of our most recent results is the conversion of pure spin current into charge current directly in graphene itself. This effect happens up to room temperature, and we can control it electrically, which makes it possible to maybe build future spintronic devices out of 2D materials and integrate them directly into existing electronic infrastructure.
The recent discovery of 2D materials that shows ferromagnetism down to the monolayer limit makes us optimistic that we will be able to create in the future a spintronic device like spin field effect transistor or spin orbit torque memories fully based on 2D materials. The number of combination of 2D material and the resulting physical properties that we could exploit to create new devices for application are quasi endless, and this is quite exciting in terms of research and developing of new technology.
As I mentioned before, one important goal for us here is that we can take our findings from the lab and bring them to the industry. In this way, we can push the boundaries of what we think is possible and tackle the problems of our society. This will bring improvement in technologies such as much efficient processors and computers, less carbon-intensive electronics, reduced power consumption in data centers, and more efficient data communications.